Okay, right. So the message came. Now we can start our discussion by using 8086 processor. So now let us start the architecture of 8086 processor and programmer's model. So this is what the first thing you should learn, so that after completing programmer's model, you will understand the internal register bank that is provided by 8086, which we can use as the operands in the instructions during the practicals. So this was missing in the last practical session, and in that session I wanted to just give you idea about the TASM software, that what is the TASM software, what are the three important components that you should be able to use, that is TASM, that is assembler, then T-Link, that is linker, and TD, that is debugger, and what is the general format of assembly language program. This is what we discussed in the practical session. Now let us begin the architecture. So first of all, you should be aware of the chip, 8086 chip, and you can see this is how the 8086 chip looks like. So it is a 40 pin IC, 20 pins on one side, 20 pins on other side. Okay. Particularly this particular notch is important in case of integrated circuits, because this notch allows us to count the pins, the direction in which I should count the pins, right? So you should see this notch in any integrated circuit, and the first pin to the left of that notch is always considered as pin number 1. So this is pin number 1, then 2, 3, 4. Like this we have to count. Here you will find this is pin number 20. And after pin number 20, pin number 21 will be considered as this pin, the pin which is on a right side of this notch. Okay, so this pin is called as pin number 21, and this last pin which will be present over here, this will be known as pin number 40. You should know how to count the pin numbers on a IC, because if somebody gives you IC and if you know the pin number, that I know that the pin number of INTR pin is this somewhere 18. So which pin is pin number 18 is not written over here on the IC. So you should be able to find out pin number 18, and that you can do by counting from this side. So from the left side of the notch, first pin will be counted as pin number 1, and then you should keep on counting. So you will reach to pin number 18, and in your circuit or the system that you are designing, you can consider this pin number 18 as the INTR pin, or pin number 20 as a ground pin, right? So you should be able to identify the pin. The topics that we are going to cover today is architecture diagram of 8086 and significance of different internal units, like execution unit is one part of 8086 processor. EU, in short, it is called as execution unit. Then BIU, that is bus interface unit. This is second part present inside 8086 processor. So EU and BIU are the two important parts. Then arithmetic and logic unit, which is part of EU, and instruction queue, which is part of BIU. So if you explain these four blocks from the 8086 processor, that completes answer to the question, explain the architecture of 8086 processor. But architecture itself will consist of one more thing, that is called as programmer's model or resistor set, that is present in 8086. So we need to cover that also. So if I wanted to look at pin diagram of 8086 processor, it is something like this. So this is a notch on the left hand side. This is pin number 1. This is ground, or this is pin number 20. This is also ground. 8086 processor has got two grounds, one for EU, one for BIU, and then every pin is numbered. Like you can say pin number 18 is INTR. Just now I have shown, I said that pin number 18 is INTR pin. Then pin number 40 is VCC. Oh, I made a mistake. So after pin number 20, this will be counted as pin number 21, and then you have to go to the top. So top right will be the last pin of the IC. So that correction you have to make. So we will see this pin diagram, because in some questions they ask you to explain the hardware model of 8086. Hardware model means you have to explain the pin configuration, and you have to explain the function or use of each and every pin. So you have to remember these 40 pins and their names. But it is not difficult to remember. Once you segregate them according to their functions, we can remember all 40 pins of this particular IC. That we will do sometime later. We'll start with the features of 8086 processor. Sometimes in short answer questions, the question can come like this: list different features of 8086 processor. So these features actually you need not have to by heart. After learning 8086, you will definitely remember all these features of 8086 processor. Like the first feature of 8086 processor is its operating frequency. This is a very important specification for any processor, that at what speed that processor works. That is nothing but what? Clock frequency or operating frequency. So 8086 processor comes in three different variations. Some 8086 processor ICs works at 5 megahertz frequency, some works at 8 megahertz frequency, and some of them works as 10 megahertz frequency. So while purchasing 8086, the seller will ask you that you want 8086 processor of what frequency, because it comes with three different variations, three different clock speeds. So you can select any, and if you want a fastest, you can select 10 megahertz operating frequency. So operating frequency of 8086 processor does not exceed 10 megahertz. That is the highest operating frequency with which 8086 processor works. So this is the thing that you should remember as one of the feature, that its operating frequency is maximum 10 megahertz. Then 8086 processor consists of arithmetic and logic unit. This is also very important specification about a processor, and the ALU of 8086 processor is 16-bit ALU. Now what does this really means? It means if I ask the 8086 processor to perform some operation on the operands, it may be, let us perform addition of the two numbers or subtraction of two numbers, then what is the maximum size of the numbers that I can process? That is decided by ALU bit capacity. So if ALU is 16-bit, that means 8086 can perform addition of two 16-bit numbers in a single cycle, or 8086 can perform subtraction of two 16-bit numbers in single cycle, or 8086 can perform comparison of two 16-bit numbers in single cycle. Okay, but if I ask you to use the 8086 processor to perform addition of two 32-bit numbers, will it be able to do it? Because we are saying the ALU capacity of 8086 processor is 16-bit, and I wanted to use 8086 processor to perform addition of two 32-bit numbers. Then yes, 8086 can perform addition of one to 32-bit numbers, but not at a time. That means it will divide that two 32-bit numbers into parts. First part, 16-bit part of first number, and first 16-bit part of second number, they can be added at a time to prepare 16-bit result. And then second 8-bit 16-bit parts of that numbers can be added separately. So addition of two 32-bit numbers cannot be performed simultaneously, but it will be performed one after another in two different cycles. But definitely 8086 processor says I can add 32-bit numbers, even I can add 64-bit numbers, even I can add 128-bit numbers. That is not a problem. But at a time, I can process only 16-bit parts of that number, not more than 16-bit parts. Therefore, the ALU specification is important. Like the Pentium processor right now we are using is a 64-bit processor. What does this mean? At a time, the Pentium processor can perform operation on two 64-bit numbers in a single cycle. So you can imagine, if I ask to do the same thing to the 8086 processor, it will require 4 times more time. It is a simple calculation. दो 64-bit number Pentium एक ही cycle में add कर सकता है. But if I ask the same task to the 8086, it requires 4 cycles because it divides the 64-bit number into 4 16-bit parts. और एक cycle में एक ही part add कर सकता है वो. So that is considerable increase in speed in Pentium as compared to 8086. तो जितना ALU का capacity होता है, that is normally specified as the processor capacity. For example, 8086 is called as 16-bit processor. 80386 is called as 32-bit processor. Pentium is called as 64-bit processor. So who decides how many bit processor it is? It is the capacity of ALU. So if ALU is 16-bit, processor is 16-bit. Previous to 8086, there was 8085 processor, which is known as 8-bit processor, because its ALU capacity is just 8-bit. It can add only 2 8-bit numbers at a time. So I hope you have understood about this specification of the or feature of the 8086. So this is important specification or feature you should list. That 8086 processor consists of 16-bit ALU. I hope simultaneously you are taking notes of whatever we are discussing in your notebook, because I'm not able to see whether you are writing or not, but it's important that whatever I am explaining simultaneously you should keep on writing in your notebook, so that at the end you will have a good set of notes prepared for exam preparations, right? Then third feature of 8086 processor, it consists of 16-bit resistors. It consists of many resistors internally, but size or capacity of every resistor is 16-bit. Like it consists of AX 16-bit resistor, BX 16-bit resistor, SI 16-bit resistor, CS 16-bit resistor. So all the resistors present in 8086, their size is 16-bit. This is also important because how big data we can store inside the processor, that is decided by the capacity of resistors which is present internally. So all the resistors of 8086 processor are 16-bit resistors. Then next feature of 8086, it provides 16-bit data bus. That means it provides 16 data lines, D0 to D15. D stands for data, so D0 to D15, 16 data lines are provided by 8086. And you know the significance of data lines. Data lines are mainly used for carrying data either from processor to outside world or from outside world to processor. Outside world means it may be a memory location or it may be input output device. So whenever processor wanted to convey data in and out, it makes use of its data bus, and through this data bus at a time maximum processor can send only 16 bits. It cannot send a data larger than 16 bit, or it cannot receive data larger than 16 bit. So if it wants to read 32 bit data, then it has to conduct two machine cycles. One for conducting lower part 16 bit data, other for getting the higher part 16 bit data from the memory location or from device. So data bus is also one of the important specification, and that will affect the performance of the system, because if the width of the data bus is large, then simultaneously large amount of data can be conveyed. Like the 386 processor has got 32-bit data bus. That means at a time it can transfer 32-bit of data, whereas 8085 is a is having 8-bit data bus. That means at a time it can transfer only 8-bit of data. So I hope this specification is important and you will remember it, that 8086 processor provides 16-bit data bus. The next specification is about address bus. 8086 processor provides a 20-bit address bus. That means its address bus consists of 20 lines, 20 pins. That is A0 to A19. A0 to A19. A stands for address. So A0 to A19, 20-bit address line is provided by 8086. So if I say it provides a 20-bit address bus, that means it can generate 20-bit addresses. How much memory it can address? Can you calculate this? As I already asked you the question at the beginning of this particular session, that if the processor provides 8 address lines, how much memory it can address? 256 bytes. Similarly, if I ask you the question, if it provides 20-bit address bus, how much location or how much address space it can address? So is it possible to calculate? It is possible. You have to calculate something called as 2 raised to 20. So to calculate the memory space, I have to calculate 2 raised to 20. So 2 raised to 20 you have to calculate that much address space it is able to address. 2 raised to 20 comes to be equal to 1 megabytes. So 2 raised to 20 is 1 MB, 1 megabytes. This B is really important. When we write this B in uppercase, then it means byte. You have to consider this as bytes when I write B in capital. But if you see the speed of the internet, many times it is specified in your mobile also. If you enable that feature when you are connected to the mobile data or Wi-Fi data, then it is continuously showing you that what is the current speed with which data transfer is happening. That is normally specified like this. That is kbps. Have you come across this particular specification, kbp/s? This is called as kilo beats per second. So if I write B in lower case, then it is not considered as byte, it is considered as bits. So this is a convention in the network theory or in a microprocessor. Whenever we write B uppercase, it is called as bytes, and whenever we write B in lower case, it is called as bits. And you know the difference between bits and bytes. A group of 8 bits will form a byte. Okay, so this is as good as, if I want to write it in form of bits, then it is 1 M into 8 megabits. This time I will write B small. So amount of memory the processor can address is 1M into 8 megabits. Why I have considered into 8? Because 1 byte is 8 bits. So if I want to have the number of bits that are addressable, that is 2 raised to 20, that is 1 megabyte, and that is equal to 1 into 8 MB. That is small b, which stands for bits. Okay, so otherwise this specification is enough that you should know that 8086 processor can address up to 1 megabyte of memory. From where this 1 megabyte came? It came from number of address lines. 8086 processor provides 20-bit address bus. So I hope this feature is clear to all. The next feature is it supports two-stage pipeline. The pipeline is a very important specification that specifies whether the processor is able to perform parallelism in the stages of instruction execution. So yes, 8086 processor supports two-stage pipeline. It can simultaneously perform fetching and execution. So when previously fetched instruction is under execution stage, at the same time it can prefetch next instruction. Why we will call it as a prefetching? Because it is fetching ahead of a time. Still the instruction is not required because the processor is executing previous instruction. So next instruction is not required yet, but still processor will fetch it from the memory. This is something called as what? Prefetching, fetching ahead of a time. And therefore when the processor completes previous instruction, it need not have to wait for new instruction to come from memory, because it has already fetched it and kept internally so that it can be taken from that location, and the waiting period of the processor can be saved, and the speed or performance of the system can be improved. So pipelining is a very important feature of a processor. 8086 processor provides two-stage pipelining, that is fetch and execute. These two stages can be overlapped, right? Then the next feature of 8086 that it internally consists of 6 byte of instruction queue. So not 6 bits, because many a times I find the student incorrectly writes 6-bit instruction queue. 6-bit is useless thing. So it consists of 6 byte of instruction queue. That means it can prefetch few of the instructions from the memory, and that prefetched instructions are stored inside this particular 6-byte instruction queue. So whenever processor requires next instruction, it doesn't run to the memory. It takes that instruction from the instruction queue. In detail about this instruction queue, we will see very soon in the architecture. Okay, so this instruction queue is the reason because of which the processor 8086 processor can perform pipelining. Because if this instruction queue is not there, then pipelining is not possible. Why? Because this instruction queue will act as a temporary location where the processor can save the instructions which are fetched ahead of time. क्योंकि अहेड ऑफ टाइम जो फेच होते हैं इंस्ट्रक्शन मेमोरी से, वो प्रोसेसर में किधर तो रखने पड़ेंगे ना, जहां से वो एग्जीक्यूशन यूनिट उठाएगा उसको. बट वो रखने के लिए अगर प्रोसेसर ने जगह ही नहीं दी है इंटरनली, then it is not possible to prefetch the instructions. Only because of this instruction queue, 8086 processor can prefetch the instructions and we can have two stage of pipelining. So this is very important feature of 8086 processor. The next feature is it provides you two hardware interrupts. Now, interrupts you might have learned in the previous course, that is computer organization. Interrupts plays a very important role because this saves a lot of time of the processor in which it might have wasted in performing polling. Now, what is this polling and what is interrupt? So, in very short, if I want to give the example, it goes like this. If I wanted to know that whatever I have explained, is it understood by the students sitting in my class? How can I understand or how can I recognize this particular thing? Whether whatever I am explaining is reaching to the student, are they getting it, are they understanding it? One way to do it is, after explaining every small topic, I should ask every student one by one, have you understood, have you understood, have you understood, do you have any doubt? So what will happen in this case? If there are 60 students sitting in my class, then I have to go through each and every student, and personally I should ask that student that whether he has understood or she has understood or having some doubt. This will waste considerable amount of time of my lecture period, right? Instead of that, what we can have other method. What I will announce at the beginning, that I will keep on covering the topic, I will keep on explaining the things in that topic. If you are having any doubt at any point of time, you can raise your hand and you can ask that query. What will happen in this case? After explaining every topic, I will just have a look at my class and I will see whether somebody has raised hand or not. If nobody has raised hand, that means I will assume that whatever I have explained is understood by the student. Many a times this can be a wrong assumption, but anyway, this will save a lot of time because I need not have to ask every student separately, have you understood or not. The student having doubt can raise hand and can ask. That is something called as what? Interrupt. Because the student raising hand is asking me to stop explaining the next topic and give attention to my query or my doubt, so that the teacher will address that particular query, and then after completion of that doubt session, the teacher can go ahead with the next topic. But this will save considerable amount of time. So I hope you have understood about interrupts. In the microprocessor system also same type of communication is used, because processor has to communicate with many input output devices, and it should not keep on asking every input output device that whether you wanted to communicate now or not. This will waste a lot of processor time. So instead of that, what processor will do, processor will keep on doing is its own operations. Whenever any input or output device wanted to communicate with the processor, that device will generate interrupt. So processor will suspend the current task that it is doing, and it will go for servicing that particular interrupt. It will service the interrupt request generated by the device, input or output device. This will save considerable amount of time for the processor. So interrupts are very important. 8086 processor provides two hardware interrupts. That means there are two interrupt pins on the 8086 processor. One is called as INTR, that is interrupt, and second is called as NMI, that is non-maskable interrupt. So INTR and NMI are two interrupt inputs for 8086 processor. So this is one of the important feature of 8086 processor. Apart from these two hardware interrupts, the 8086 processor also provides software interrupts or vectored interrupts. So it provides you 256 software interrupts. So these are called as vector interrupts, or these are also called as software interrupts. So there are two hardware interrupts and 256 software interrupts. Software interrupts means they are in form of instructions. So in my program, anywhere if I want to generate interrupt to the processor, I have to incorporate the interrupt instruction in my program. So I think you are going to hear a little noise. This is because of the municipality drive for the disinfection. So let us wait. Now it has gone. Okay. So software interrupts are in form of instructions. We have to incorporate them inside our program. So whenever processor execute that interrupt instruction, it will go for servicing that interrupt. So it provides you 256 vectored interrupts or software interrupts. So this is one of the important feature of 8086 processor. Apart from this, 8086 processor has got many features, and you can add them as and when you come to know about them during our discussion. So deliberately I have not listed all the features. I have listed only few of them. Around 9 I have listed. But this is not all. It has got other features also, and you should be able to understand them and list them as and when I will discuss as and when I discuss them along with you. So I hope this particular topic is clear, that is features of 8086 processor. The question that can be asked in the exam is list different features of 8086 processor. We have listed 9 right now. Apart from these 9, others are also there, which we will list very soon, right? So now we will move on to the next point. Now what I wanted to show you is the architecture of 8086 processor. As I already told you, the 8086 processor is internally divided into two parts. One part is called as bus interface unit. In short, it is called as BIU. That is bus interface unit, BIU. So this is one part of the architecture of 8086 processor, and the other part is execution unit. In short, it is known as EU. EU stands for execution unit. So the first thing that you should write, that the 8086 processor internally consists of two working units. One is called as bus interface unit and other is called as execution unit. And you can add this as one of the feature in the previous question, that 8086 internally consists of two working units. One is called as BIU and other is called as EU. So this feature I have not listed in the previous slide, but you can list this in your notebook, that 8086 processor consists of two internal working units. And then if I show you the diagram of internal architecture of 8086 processor from book, I have picked it. It appears something like this, and you can see clearly there are two parts. One part is known as BIU, which is written over here, bus interface unit, and second part is called as EU, that is execution unit. And there is a boundary which separates these two parts. The boundary goes like this. So there are two internal units, bus interface units and the execution unit. So we need to write the answer to the question, draw and explain architecture of 8086 processor. This is a 10 marks question asked many times in the university question papers. Draw and explain architecture of 8086 processor. But before we jump to the architecture of 8086 processor, this looks to be looks like a very complicated diagram. Actually, it is not if I divide it into parts, and we will learn that parts one by one. So instead of going or jumping directly to the architecture of 8086 processor, what I wanted to first go through is this part. So if you are able to see this part in the architecture along with this resistor, so if I discuss only this part of the processor architecture, this is something called as software model of 8086, or it is also called as programmer's model of 8086. And this is also asked as a separate question, that explain the programmer's model or software model of 8086 processor. So we will first address that question, that explain the software model of 8086 processor. And it goes like this. It consists of these resistors, these resistors, these resistors, and flag resistor. So now in your notebook you can give the heading software model or programmer's model of 8086 processor, because this is also a 10 marks question asked many a times in the university question papers. So give this heading software model of 8086. And now let us start explaining the software model of 8086. Right. The software model of 8086 processor consists of set of internal registers which can be used in the instructions by the programmer. Software model of 8086 processor consists of set of internal registers which can be used in the instructions by the programmer. So whenever we wanted to write program for 8086 processor, we wanted to write set of instructions, and instruction consists of two things, that is operation and second is operand. Every instruction requires two things, operation and operand. So operation can be move and operands can be ax comma bx. So what is this ax comma bx? Ax is an internal register, bx is an internal register, and they are acting as a source and destination operand for my instruction. So the software model of 8086 processor is nothing but the set of registers, internal registers, which can be used in the instructions by the programmer. So I hope you have understood the definition of software model. And then you have to list out different registers and their significance as far as the instructions or programmer is concerned. Because when we want to write any program, we should know the significance of the register that is available to us, which we can use for storing operand or for storing the result. So it goes like this. This is the architecture of 8086 processor I have shown you. So now we are concentrating only on this part, and we are going to expand this part as a software model. So you can see, if you carefully see this diagram, it consists of this AH, AL, BL, BH, BL, CH, CL, and DH, DL. These are called as the GPRs. The 8086 processor consists of 4 GPRs. GPR stands for General Purpose Registers. 8086 processor consists of 4 GPRs, that is General Purpose Registers. This should be your first point whenever you are writing answer to the question software model. And then you should draw the diagram, but the complete diagram you will draw at the end. Do not draw it right now. Just understand all the things, and then I will give you time to draw this software model diagram, right? So then the first register that we have to go through is a AHAL, pair of two 8-bit register. AH is a 8-bit register. AL is also 8-bit register, and if they are combined together, then they will form a 16-bit register known as AX. So AX is a 16-bit register, and it consists of two 8-bit parts, that is AL and AH. So now we started writing about AX register. So after writing the 8086 processor consists of 4 GPRs, next point you will write is the first register is AX. Right, the AX is a 16-bit register which can be divided into two 8-bit parts, AL and AH. AX is a 16-bit register which can be divided into two 8-bit parts, AL and AH. I hope you have written this in your notebook. Now, I know the name of the resistor, I know its capacity. Now, I should know what is its significance. So right, the next point, the Ax resistor can be used as a 16-bit operand in 8086 instructions. Ax resistor can be used as a 16-bit operand in 8086 instructions, or it it can be used as a 8-bit resistor in form of Al or Ah, or it can be Ax can be used as a 8-bit resistor in form of Al or Ah. That means in the instruction I can use Al as the operand, there will not be any problem. I can use AH as an operand, there will not be a problem. Or I can use AX as an operand, there cannot be any problem. So AX register has given me the flexibility that if I want to store and process only 8-bit operand, then why to use AX completely? You can use either AL or you can use AH. But if I wanted to store and process 16-bit numbers, then we cannot use AL and AH. Rather than that, we have to use AX as the register name. For example, if I want to store one number, let's say 2C58H, this is a number which I wanted to store. This number I cannot store into only AL, or I cannot store in only AH. Why not? Because this is a 16-bit number. How we will come to know that this is a 16-bit number? Because when somebody gives you hexadecimal number, this H stands for hexadecimal. When somebody gives you hexadecimal number and asks you to find out how many bit number it is, the logic is very simple. Every hexadecimal digit corresponds to 4 binary bits. Every hexadecimal digit corresponds to 4 binary bits. For example, the 8 is one of the hexadecimal digit present in this number, and it corresponds to binary bit pattern, that is 1000. So every hexadecimal digit corresponds to 4 bits. Like 5 corresponds to 4 bits, that will be 01001. Then C is also consisting of 4 bits, that is 1100. 2 is also 4-bit number which consists of bits 0010. So if I count, so it is 4 plus 4 plus 4 plus 4, 16 bits. So I wanted to store this 16-bit number, and if I wanted to store a 16-bit number, I have to make use of AX. I cannot make use of AL or AH because their capacity is just 8 bits. Now, this 16-bit number, if I write in the binary format, it is something like this. So this corresponds to 8, this corresponds to 5, this corresponds to C, and this corresponds to 2. So if you count the number of bits, you will find they are equal to 16. And then if I write the instruction to store this number into Ax register, what will happen is this, that the lower byte, this is called as lower byte LB, the lower byte of the number will be stored into AL part of AX, and the higher byte of the number, that is 2C, this is higher byte, this is going to be stored inside higher part of the AX, that is nothing but what? AH. So AH will hold 2C, this 2C will be stored inside AH, and this 58H will be stored inside AL, and together they will form a 16-bit number which is known as AX. So I can say AX is now storing a number that is 2C58H. Is this clear? Like this, that higher order part is 2C which is stored in AH, and lower order part 58 that is stored in AL. So this flexibility is there. After storing them like this, can we process only this part of the number? The answer is yes. Can we process only this part of the number? The answer is again yes. Can we process this as a 116-bit number together? The answer is yes. So you can see a lot of flexibility is provided because of dividing the 16-bit register into two 8-bit parts. Is this clear? So in my program, I can very well write instruction like this, like move. I can write move. Move is nothing but what? The mnemonic. I can write a destination let's say destination is Ax, and then directly I can specify the number as a source which I wanted to store. The number that I wanted to store is 2C58. So I can write 2C58H directly as a part of instruction. So if I write this instruction in my program, this number 2C58H will be stored in the Ax register like this. Or this operation can be performed by using two instructions. What will be that two instructions? I can write instruction to store only this part into AL and only this part into AH, so that together AX will hold 2C58H. I hope you understood how to load this register with some value. Clear? What is its significance? It is used, or it can be used as one of the operand while performing arithmetic and logical instructions. So whenever we are performing addition, subtraction, one of the operand can be Ax. It can be also used for storing the result of arithmetic instructions. Or whenever we wanted to perform logical operations like AND or NOT, rotate, shift, then also we can use Ax as one of the operand, or Al as an operand, or Ah as an operand. So it can be used as an operand for arithmetic and logical instructions. This is one of the use of Ax register. See, you have to write or mention the use of the register also. So whatever I have shown over here, this is even if you don't write, it is okay in the answer, because this I have explained only to give you idea that how the register will get loaded if I wanted to store some number into it. So right from the beginning you will have a clear idea how the registers can be used for storing the number and which part goes where. So that is important. Now I am explaining the use of the Ax register. First use I have told that it can be used as an operand for all arithmetic and logical instructions, right? Then the second important use of Ax register is in case of multiplication instruction. In case of multiplication instruction, this is very important. Ax or Al is considered as default operand. In case of multiplication instruction, if I am performing 8-bit multiplication, then AL will be considered as one of the default operand. And if I am performing 16-bit multiplication, then AX will be considered as one of the default operand. Now, what does this mean? Default operand, right? So I will quickly like this. Suppose I wanted to perform addition of two numbers. So when I wanted to perform addition of two numbers, I have to make use of the instruction that is known as add, and we need to specify two operands. I can specify two operands like this. Ax is one of the operand, comma, I can specify second operand, let's say bx. So if I write this instruction, then the processor will perform addition. It will add the contents of bx into Ax, and the result will be kept inside Ax. So what are the two operands we used for the addition? Ax and bx. And do we need to specify Ax exclusively as a part of instruction? Yes. It is not a default operand. It has to be specified exclusively, explicitly inside the instruction. But when I want to perform multiplication of two numbers, and when I write something like this, there is an instruction called as MUL, stands for multiplication. Mnemonic is MUL. And then I have to specify only one operand. I cannot specify two operands for mul instruction. Now, if I specify BL as that operand, if I write instruction mul, then I have to specify only one operand. And if I specify BL as the operand, BL is a 8-bit register. You can see it over here. BL is a 8-bit register. So now, by default, processor will multiply contents of AL with BL, and the result will be stored into AX. Are you getting what I am saying? Mul BL instruction, what it will perform? It will perform like this. it will be multiplying AL. So let's look at left hand side. There I am having space. So AL will be multiplied by BL. And if I multiply two 8-bit numbers, it may happen that result may exceed 8 bits. So the result is by default stored in AX, not in AL. By default, it will be stored in AX. So in the instruction, have I mentioned AL as the operand? I have not mentioned. By default, processor has taken it as one of the operand. That means if I want to perform multiplication of, let's say, CL and BL, can we perform it directly? The answer is no. We cannot directly multiply BL and CL. To perform multiplication of BL and CL, one of these two resistors I have to move into AL first. So I may move BL into AL, and then I may write instruction mul CL. Then it will perform CL multiplied with AL. The result will be stored in AX. So what is the use I specified? In case of multiplication instruction, 8-bit multiplication uses AL as a default operand, whereas 16-bit multiplication uses AX as a default operand. Means what? Instead of writing mul BL, if I write mul BX, now what? The second operand that we have specified is a 16-bit operand. So this will not perform 8-bit multiplication. This will perform 16-bit multiplication. Now the multiplication performed will be somewhat like this. Now look at the left side of the slide. It will multiply contents of AX, not AL. It will multiply contents of AX with the contents of BX to prepare the result. And since I am multiplying two 16-bit numbers, result may exceed 16 bits. So the result will be stored in the DX combined with AX, because only AX is not sufficient to hold the result now, because capacity of AX is just a 16-bit and result may exceed 16-bit. So the result will be stored into two parts. Lower 16 bits are stored into AX, higher 16 bits will be stored into DX. So you might have understood now what is the special use of Ax resistor or AH resistor. You cannot use any other resistor for this purpose. By default, multiplication instruction uses AL or AX as the operand. As well as you can say by default, multiplication instruction uses AX as destination for storing the result. By default, multiplication instruction uses AX for storing the result. So I have specified 3 points now. Now, the next important use of Ax resistor is, in case of division instruction also, Ax is used as default operand. Now I am not saying AL. Listen to me carefully. Every word that I am saying is important. Don't have your own assumption. Multiplication में AL या AX हो सकते हैं default, but in division only AX will be used as a default operand, and it is always used as a numerator. In case of division, only AX is used as a default operand, and it is always used as a numerator. Means what? For example, wait. Okay, so I'm just finding a space to clear the things. Anyway, so when I write the instruction, I will write it over here. When I wanted to write division instruction, the division instruction can be framed like this in 8086 processor. I have to write div. This is a mnemonic, and with the div instruction, I can specify only the 8-bit operand like this. I can write div bl. So when I write div bl, it will perform division. But to perform division, we require two operands, and we specified only one, that is BL. So who will be the other operand? By default, AX will be considered as other operand. So this div BL instruction will perform division like this. It will divide the contents of Ax resistor, 16-bit contents of Ax resistors will be divided by 8-bit contents of BL resistor. So now you can see Ax will by default act as numerator for this division, and the resistor that we are specifying over here will act as denominator. So division instruction in detail we will see later on. As of now, you should just remember the special use of Ax resistor, that in case of division, Ax is by default used as a numerator operator. Is this clear? 8-bit by 8-bit division is not supported. 16-bit by 8-bit division is supported by 8086 processor. How and why we will see later on. So I hope you have understood this use of Ax resistor. Now next use of Ax resistor is whenever processor wanted to perform input-output operation with the I/O device, whenever the processor wanted to perform input-output operation with I/O device, then by default Ax can be used as the register through which data can go out or a register in which data can be received. Are you getting what I mean to say? Suppose processor wanted to read the data from a keyboard, then whenever we type a key on a keyboard, the key code, character code of that particular character is by default received in Ax. You cannot use other register for doing this, Al or Ax, but not other. And if I wanted to display some character on the screen, that means output device, by default I should load that character into Al or Ax, and that will be displayed on the screen. So in case of input output operation, so you can write this as a point. In case of input output operation, Al or Ax are used as default operand. Al or Ax is used as default operand. So this is a special use of Ax or Al resistor. So I hope you have listed all the special use of Ax resistor, right? So I will have a short break of, let's say, 5 minutes. You can think about whatever we have discussed up till now. Just update your notebook about the points that we have discussed, and we will resume. Just a 5 minute break to so that you will get refreshed. Okay. So I'm back again. I hope you have refreshed. We will continue with the remaining part of our presentation. So if you remember, we are here. Okay, this is what we have discussed up till now about Ax resistor. So Ax resistor is over. I have explained what is its use and the specific, you can say, purpose of having this resistor in the register bank of 8086. Right? Everybody is back. We will move on to the next resistor, that is called as Bx resistor, and you can see it is also a general purpose resistor which is divided into two 8-bit parts, that is BL and BH. Combined together it can form one 16-bit resistor known as Bx. The Bx resistor can be used as the operand in arithmetic and logical instructions. Like I have already shown you, in add instruction I have used Bx, multiplication instruction I have used BL or BH, division instruction I can use BL or BX. So it can be used as an operand in arithmetic and logical instructions, that you can say as one of the use of Bx resistor, and it has got one special use that you should understand. The Bx resistor can be used to provide offset of the memory location present in data segment. Now, this you should write very carefully in your notebook. Bx resistor can be used to provide offset. Now, what is offset? We will see. You just first complete the answer. The Bx resistor can be used to provide the offset of the memory location present in data segment. It can be used to provide offset of a memory location present in data segment. This is the specific purpose or specific use of Bx resistor, which is not true for Ax. Ax cannot be used to provide the offset. Only Bx can be used to provide the offset of a memory location present inside data segment. So what is this? We will see in the addressing modes. Otherwise, Bx will be similar to Ax. It can be used as a 8-bit operand, BLBH, or it can be used as a 16-bit operand. So specific use is offset, right? Then the third resistor that you are able to see is CL and CH. So CL is 8-bit, CH is also 8-bit, and combined together this is 8-bit part CL, this is 8-bit part, that is CH. Combined together they can form one 16-bit resistor known as CX. So CX is a 16-bit resistor. What is the use of CX resistor in the 8086 programs? So Cx resistor can be used as an operand for arithmetic and logical instructions. This is same as Ax because it is a general purpose resistor, and general purpose resistors are mainly used for holding the operand or for holding the result. So it can be used as an operand in arithmetic and logical instructions supported by 8086. That use will remain common for all Ax, Bx, Cx and Dx. What is specific use of Cx? That you should understand. Specific use is it can be used as a counter. So C stands for counter basically. It can be used as a counter for the looping instructions. There is an instruction known as loop, LOOP. So loop is one of the instruction of 8086 processor. And then how many number of times you wanted to perform looping repetitions will be decided by the number present in CL register or Cx register. So it can be used for looping instructions, as well as it can be used to provide count for rotate and shift instructions. It can be used to provide count for rotate or shift instruction. So you might have heard left shift, right shift operators in C or in Java. I hope you remember left shift operator and right shift operator. So they are operators in C or Java, and left shift operator shifts every bit of the operand towards left, by specified number of positions. So how many number of positions you wanted to shift, that is normally specified by CL register in 8086 assembly language. So I can write instruction known as, let's say, ROL. ROL stands for rotate left, and then rotate left I have to specify operand, that is, let's say, BL, and I have to specify by how many number of bits I wanted to rotate by putting that count inside CL. So rotate and shift instructions can use CL register as a default counter. I need not have to specify. By default they will use CL as a default counter. Rotate instruction also uses loop instruction, is also there for looping. It is used as good as for loop in the C or in a Java. If I wanted to execute one set of instructions again and again, then at the end of that set I can put loop and I can give a label, so it will take a jump to that label again and again until CL is not 0. The moment CL becomes 0, the repetitions will be stopped. In a program, you will understand it in a better way. So we'll see a short example of this usage later on. But you should remember, specific use of CL or Cx is, it is used as a counter, default counter in many instructions such as loop, rotate, shift. Clear? So this is a specific use of Cx register, and I hope you have noted it. Then the next general purpose register we have to look after is Dx register, which is also divided into two parts, DL and DH, two 8-bit parts, DL and DH. Combined together it can form one 16-bit register, that is Dx. And again it is a general purpose register, so we can say first use is it can be used as an operand in arithmetic and logical instructions to store the operand or to store the result. So it is a general purpose register. What is the specific use of Dx register? That is important. So next use of Dx register is multiplication instruction uses Dx register as a default destination. Multiplication instruction uses Dx register as a default destination if the result is exceeding 16 bits. So I hope you are writing and write it very clearly. The multiplication instruction uses Dx register as a default destination if the result exceeds 16 bit. Like in this case, I have already explained the case in front of you. So whenever I perform multiplication of Ax and Bx, just a minute. Hello, good morning, sir. Okay, so sorry for the interrupt. I have got the call from our director, sir, Milind sir, so I have to attend. So I hope you all are here and still waiting for me. So thank you. But this is something called as interrupt. You can see. If the interrupt is important, I can suspend the current task and I can service the current interrupt request. And then again, of course, we can resume. So now we are discussing about DX resistor, and if I'm not wrong, I have specified one of the special use or purpose of the DX resistor. That is, by default, multiplication instruction uses DX resistor for storing the result, provided it exceeds 16 bit, right? If the result is accommodated in 16 bits, then only AX is used as a destination. But if it is exceeding 16 bits, then the higher bits, higher order bits of the result, which are exceeding the 16 bits, they are not dropped. They are stored inside DX register by default. Even if I have not mentioned it in the instruction, of course, we cannot mention it. By default, processor will do that operation for us. For example, again, I will come back to this example. I have written an instruction for multiplying AX with BX. And since AX and BX both are 16-bit numbers, there is a very good chance that the result will exceed 16 bits. Then lower order 16 bits of the result will be stored in AX. Higher order bits are stored inside DX. So it is a default destination for multiplication instruction. I hope this particular use, special use, is noted by you. The next special use of the DX register is the division instruction. By default uses DX register as a numerator, provided the denominator is 16-bit register. Now again, very specifically, you have to write each and every word that I am saying. The division instruction by default uses as part of numerator. DX register is used as a part of numerator if the denominator is 16-bit number or 16-bit operand. For example, so I should write this instruction so that you will not have any confusion. Of course, in detail, we will see the working of div instruction when we will go to the instruction set. But here, unless I do not explain the case, you will not understand its special use. For example, if I write the div instruction something like this, div Cx. If I write an instruction div Cx, that means I wanted to perform division. One of the operand I specified is Cx, and you know Cx is not a 8-bit register. Cx is a 16-bit register. The register that I have specified in the instruction will by default act as denominator. So Cx will by default act as a denominator for the division. The question is what will be used as a numerator. So by default Ax is used as a numerator, but Ax is just a 16-bit register, and 8086 processor doesn't allow 16-bit by 16-bit division. It doesn't allow 16-bit by 16-bit division. It says whenever you wanted to have 16-bit division, the numerator should be 32-bit, denominator can be 16-bit. So, but I don't have any 32-bit register present inside 8086. So what the 8086 processor does, the contents of DX combined along with contents of AX, together it will be considered as a numerator, by default numerator, and this will form a 32-bit contents. These 32-bit contents will be divided by 16-bit Cx register. This is allowed, but I cannot divide 16-bit AX by 16-bit Cx. This is not allowed. Like I already said that when we write div BL, BL will act as a denominator, and you know BL is 8-bit register. I cannot have AL or AH as the numerator, because if I take AL as a numerator, AL by BL is 8-bit by 8-bit division. This is also not allowed by the processor. So 8-bit by 8-bit division processor doesn't allow. 16-bit by 16-bit division processor doesn't allow. If at all I wanted to divide any number by 8-bit number, then numerator has to be 16-bit, and by default it is AX. Or If at all I wanted to divide any number by 16-bit number, that means denominator is 16-bit, then I have to have 32-bit numerator, and in this case dx will by default combined with ax to form a 32-bit numerator. I hope little bit about whatever I have said is clear in your mind. So you please note that in case of division instruction, by default dx is used as part of numerator to perform 32-bit by 16-bit division. So this point you should note in your notebook. So I explained the 4 GPRs, general purpose resistors, AX, BX, CX and DX, and I hope their uses is clear to all. Now let us move on to the next resistors that are present inside 8086 processor. There are 2 index resistors. So these are called as index resistors in 8086, index. So now next point you should write in your answer to the programmer's model is the index resistors. Now you should write the 8086 processor provides 2 16-bit index resistors. 8086 provides 2 16-bit index resistors. One is called as SI. S stands for source. S stands for source. I stands for index. So it is a source index resistor, and DI, that means destination index resistor. DI stands for destination. D stands for destination, I stand for index. So the 8086 provides a 2 16-bit. You can see the width. It is from here to here. It is 16-bit resistor. So SI and DI, source index and destination index resistor. SI and DI resistor has got the general purpose use. They can be used as the operands in the arithmetic and logical or data transfer instructions. So that is one use of SI and DI. Means what? I may write instruction by using SI, something like this. I can write move, let's say SI, that means SI is used as a destination, comma, I can specify any source, let's say AX. So what will happen in this case? The 16-bit contents of AX resistors will be copied into SI register. That means SI can be used as a operand for the data transfer instruction. Move is called as data transfer instruction. Or even I can use SI as a part of arithmetic instruction. I may say like this, let's say INC. INC stands for increment, and I can write SI. So if I write INC SI, what will happen? The 16-bit contents of SI will be incremented by 1. That means we have performed addition. So SI and DI, they can be used as a general purpose resistors in data transfer and arithmetic and logical instructions. This is one use. The special use of this resistor, these resistors, is in string instructions. So this is very important. There is one set of instructions in 8086 which are called as string manipulation instructions. So you know the string. What is a string? String is a sequence of characters. String is a sequence of characters. So in 8086 programming, we can process the strings like we did it in C or in Java. In C or in Java, you might have written programs to perform reversing of the string. Then you might have written a program to check the string is palindrome string or not. Or you might have written a program to convert the case of the characters in the string. Or you might have written a program to search the frequency of a particular character inside a string. So these all programs you have already written in C or in Java. Same kind of programs we can complete by using assembly language, also by using instructions in the group called as string manipulation instructions. So you know string is going to be an array, character array. So whenever we wanted to store and process a string, we require array of characters. And then the first character will be stored at index 0. Last character is stored at last index, that is n minus 1, if length of the string is n characters. And then one by one we can pick the character and we can process it. So normally when I wanted to copy a string from source location to destination location, when we wanted to copy a string from source location to destination location, then we need to point a character in the source string. This indexing, that is pointing a character in the source string, can be performed by using SI. And at the same time, we should point the character in destination string, because there we wanted to copy the source character. So we wanted to have index in destination string also. That is normally performed by using DI. So therefore the names SI and DI. So SI is mainly used to index the character in a source string, whereas DI is normally used to index the character in destination string, and they are by default used by string manipulation instruction. For example, there is a string manipulation instruction. Of course, in detail, we will learn string manipulation instructions later on. There is an instruction in 8086 instruction set whose mnemonic is like this: move SB. There is no space. Move SB. So this is one of the instruction of 8086 processor. Move SB. Move string byte. Move SB stands for move string byte. And with this instruction, I need not have to specify any operand. We cannot specify any operand with this instruction. And you know, move SB means moving string byte. There should be some source byte. There should be some destination byte. And then I have not specified them in the instruction. So how the 8086 processor will know who is source byte and who is destination byte? By default, what the 8086 processor will do, the byte pointed by SI will be considered as a source byte. Byte pointed by DI will be considered as a destination byte, and it will perform transfer. So you need not have to specify them in the instruction. Therefore, I said they are used as a default registers, default source index and destination index registers inside string manipulation instruction. So I hope you have understood and written this special use of SI and special use of DI. So SI is used for source indexing, DI is used for destination indexing, right? Now, the next registers that we need to look after, they are SP and BP. These are called as pointer registers. SP and BP are called as pointers. The P there is indicating pointer. So there are two pointer registers present inside 8086, two 16-bit pointer registers present inside 8086 processor. One is known as SP, that is stack pointer. S stands for stack, and BP, that is base pointer. So this is a stack pointer. So I will just write it over here so that you will remember the long form. S stands for stack. So it is a stack pointer, and BP, B stands for base. So it is a base pointer. So there are two 16-bit pointer registers inside 8086 processor. Okay, and then apart from these two pointer registers, that is SP and BP, what is their use? I will explain in a while. There is one more internal register that is called as a flag register, which is also a 16-bit register. And then this completes the software model of 8086 processor. Of course, the use of SP and BP is still pending, and flag is also pending. So I will explain them. But before that, what I want, you should draw this diagram in your notebook. So if the question comes like this, explain the software model of 8086 processor, draw and explain the software model or programmer's model of 8086 processor, then you need not have to draw this complicated architecture diagram. This complete diagram is not expected. Only this diagram, which I have drawn centrally, is expected, which gives the diagram of each and every register. So you complete this diagram, and we will continue in 5 minutes. So till that time, you complete this diagram in your Okay, I hope you have completed this diagram. That is the software model of 8086. Yes, all of you have completed it in your notebook.
Yes, sir.
Okay. So now what is pending is we need to write about the stack pointer and base pointer, isn't it? So you start writing about SP and BP. These are basically pointer registers which are used to access the memory locations from stack segment. These registers are used as a pointer registers for accessing memory locations from stack segment. So segmentation is one of the feature of 8086 processor which we have not discussed up till now, but that carries a lot of importance. That in the features, if you want, you can add this point that 8086 processor supports memory segmentation. It supports 4 segments in its memory. One is called as code segment, other is called as data segment, third is called as stack segment, and fourth is called as extra data segment. So 8086 supports 4 segments in the memory. So it supports segmentation. So next stage of segmentation is called as paging, which you might have already learned that memory is logically divided into partitions. That partitions are called as pages. Maximum size of a page can be 4 kilobyte, and the virtual memory concept is possible because of paging. There will be page replacement algorithms like least recently used or most frequently used or that kind of a thing. So there switching of pages from main memory to secondary memory. Secondary memory will be known as what? Virtual memory. So these all concepts, is my voice is clearly audible?
Yes, sir, it is.
Okay, okay. Because I am getting some error message over here, the network regarding network quality, so I asked. Anyway, so just recall these all things which you have learned in computer organization. I suppose you already aware of this fact, the particular paging process, virtual memory and paging. In detail, we are going to learn this again in 386 processor. So paging is the feature of 386 processor. It is not there in 8086, but 8086 supports segmentation. So you may add that as a feature in 8086 processors features list that we have completed at the beginning. So SP and BP, let us come back to the SP and BP. They are used as a pointer registers for accessing memory location from stack segment. Okay. SP, that is stack pointer, is used for sequential access of stack. SP is used for sequential access of stack, and it is used by default by push and pop instructions. So in the instruction set of 8086 processor, there is an instruction whose mnemonic is push. So you might have heard about this push and pop operations in algorithms also. So I may write push bx. So when I write push bx instruction, bx will act as source. Its a contents will be pushed. But who will act as destination? I have not specified destination in the instruction. So by default, memory top of the stack memory location TOS, it is called as TOS. Top of the stack memory location, which is present in the stack segment, which will act as the destination. And who will give me the offset of that TOS? The offset of TOS is always given by SP. And you know, whenever we push the data on the stack pointer will be updated so that there will be a new top of the stack. I hope you are able to recall these all things which you have learned in the data structure, because you might have already implemented stack, you might have already implemented linked list, you might have already implemented queue during your data structure course, right? So stack can be sequentially accessed by using push and pop instruction, which makes use of SP as a default pointer inside stack segment. So this is regarding SP. So by using SP, the stack memory or stack segment can be accessed sequentially, and which is the characteristic of the stack, which is called as what? Last in, first out, LIFO. Last in, first out. Whoever is present on top, that can be retrieved first, because that has arrived last. Because the thing which has arrived first in the stack, that will be at the bottom, and the newly arrived thing inside the stack, that will be at the top. So that is lastly came operand or data which I can retrieve first. And if I want to retrieve something from in between, then by using this sequential access, there is a limitation. I cannot directly retrieve something in between. I have to go on retrieving the things which are above it, and then I can reach to the location or the data which I wanted to retrieve, and then I can retrieve it. So this is, you can say, one of the time consuming process, but the 8086 processor has provided alternative also. In 8086 environment, we can have the random access to the stack memory. That is possible, and it is possible by using another pointer register that is known as base pointer. So base pointer register is or can be used to perform random access inside the stack segment or stack memory. So SP is used for sequential access and BP is used for random access. Both are related with the stack memory. Okay, so you should have mentioned this in your notebook. This completes SP and BP also. And now we have to move on to the next important register which is present inside the architecture or software model of 8086. That is flag register. And the flag register plays very important role whenever I have to perform decision making or whenever I have to perform looping. Because whether to select a particular branch or reject a particular branch is normally decided by observing flag, or whether the repetition is required to be continued or it has to be stopped is also decided by observing status of a particular flag. So flag plays very important role in the assembly language programming. By using contents of flag register, we have to take a lot of decisions. So we will see in detail about the flag register. Now again, this can be a separate question asked in university question paper, that draw and explain the flag register of 8086. This is asked many times in the past university examinations, right? So we will see in detail the flag register of 8086 processor. So you can see this is a flag register of 8086 processor, and I have numbered every bit present inside it. So by just observation, you can say the 8086 processor consists of 16-bit flag register. So now we started answering one small question, that draw and explain the flag register of 8086. This can be considered as a small question or even a long answer question for 10 marks. So it depends upon your luck whether they are asking it for 6 marks or for 10 marks. You cannot reduce the answer. You have to write everything, whether it is for 6 marks or 10 marks. So therefore I said it depends upon your luck. If they ask for 10 marks, then you are lucky that for this simple question you are going to earn 10 marks in the examination, right? So it is a 16-bit register, out of which few bits are not defined. That means they are not used as a flag bits. So I have already crossed them, like bit 1, bit 3, bit 5, bit 12, 13, 14, 15. They are not used as a flag bits. Whereas the bits I kept with numbers, these bits are used as a flag bits in 8086 processor. So you can count them. Out of the 16 bits, how many bits are active as a flag? So it is 1, 2, 3, 4, 5, 6, 7, 8, 9. You should write next point in your answer. Out of the 16 bits, 9 bits are active as a flag bits. Out of the 16 bits, 9 bits are active as a flag bits. Now, these 9 bits are classified into two categories. 9 bits which are active flag bits, are categorized or divided into two categories. One is called as status flag group and other is called as control flag group. So I will just highlight. So now you are able to see some of the flag bits in green color. These flag bits are called as status flags. So out of the 9, 6 bits if you count, this is 1, this is second bit, this is third bit, this is fourth, this is fifth, and this is sixth. So these 6 bits out of 9 are used as a status flags. They are used for indicating status. What is status flags we will see. And remaining 3 bits, that is these 3, D, I and T, these are used as control flags. So next point you have to write in your answer. Out of the 9 active flag bits, 6 bits will act as status flags and 3 bits will act as control flags. And the list is like this. So this is a list of 6 status flags and 3 control flags. So you can see carry flag, that is C. Then parity flag that I mentioned as a P. Then auxiliary carry flag that I mentioned as a AC. Then zero flag that I mentioned as Z, sign flag which I mentioned as S, and overflow flag which I mentioned as O in green color if you see. These are called as status flags, whereas trap flag which I mentioned as a T in the diagram, then interrupt flag which I mentioned as I in the diagram, and direction flag which I mentioned as a D in the diagram. These 3 are known as control flags. Now you need not have to give the list right now, because anyhow we are going to explain each and every flag individually, so that will cover the list. What is important here is you should know the difference between status flag and control flag. Now you should write next flag. Next point, the status flags are used by processor. This is very important. The status flags are used by processor to indicate the status of result. Status flags are used by processor to indicate the status of result. The programmer can use them to perform decision making. The programmer can use them to perform decision making. So status flags are used by processor. This is important. And then control flags are used by programmer. We are writing about control flags. Control flags are used by programmer to control the actions performed by the processor. Control flags are used by programmer to control the actions performed by processor. So I hope you have written it. Control flags are used by programmer to control the actions performed by processor. So it is for controlling the actions performed by processor. So therefore they are called as control flags. How they will control the actions performed by the processor, we will see in the explanation of that particular flag, right? So now we will go ahead and we'll see the explanation of every flag. Most of them are, I think, known to you, but still we will continue and we will see that what is the significance of every flag. So again, I will draw the flag register. I will not show the unused bits. They are kept blank. Used bits, I have given names to them. And one by one, we will write about every flag. We'll start with a carry flag. This flag is set when there is a carry out of most significant bit in case of addition or borrow in case of subtraction. So if addition of two numbers or subtraction of two numbers, in case of addition, it may generate carry. In case of subtraction, it may generate borrow. So if the arithmetic operation, addition or subtraction that we have completed previously has resulted into carry or borrow, then this is indicated by setting this bit. Otherwise, this bit will be clear. It means what? For example, if I consider 8-bit number, something like this, let's say, 1001 and 1101. This is, let us assume, contents of AL register. And if I consider another 8-bit number, let's say BL. So if I write 1000 and let's say 0, 0, 1, 0. Now I have taken two 8-bit number. Please excuse me for the handwriting because I am writing by using mouse pad. Okay. So if, but I think it is clearly visible. If I want to add these two numbers, that means arithmetic operation I am performing. Bit by bit the processor will perform addition. So 1 plus 0, the result will be 1. 0 plus 1, the result will be 1. 1 plus 0, the result will be 1. 1 plus 0, the result will be 1. 1 plus 0, the result will be 1. 0 plus 0, the result will be 0. 0 plus 0, the result will be 0. And now 1 plus 1, the result will be 1, 0. Out of 0 will be present in AL and 1 is forwarded as a carry. So whenever this type of carry is generated by the addition, then automatically carry flag will be set to indicate that the result, this is 8-bit result. The 8-bit result, which I can say 0001 means 1 and 1111 means F. So addition of these two numbers will result into 1F, which will be present in AL register. But this is not the complete result. This is the part of the result. One bit of the result, higher order bit of the result is missing. That is carry generated, and that is indicated by setting carry flag. So who will set the carry flag? The answer is processor will set the carry flag. How? After performing addition, if the most significant bit, addition of most significant bit has resulted into a carry, then the carry flag will be set. It is that simple. Have you understood and written the explanation of carry flag? This flag is set when there is a carry out of most significant bit in case of addition or a borrow in case of subtraction, right? So this is a carry flag. Then the next flag we will explain is known as parity flag. So you might have heard about the parities. There can be two types of parities. The parity can be either even parity. Have you heard about even and odd parity? The parity
Yes,
can
sir.
be, yes, sir. Okay, the parity can be even parity or the parity can be odd parity. So when do you say the parity is even?
When the number of ones are even.
Right. So if we say that we have performed some arithmetic or logical operation which has resulted into some number. So let's say one 8-bit number is a result of the addition or subtraction. Let's say this example. So result is 1F. This one is not considered because it is not stored in AL. It has gone into carry. So don't consider this one. So in AL, what is there is 000011111. So then if I ask you what is the parity of this number, you will say the parity of this number is odd because it consists of odd number of ones. If it consists of even number of ones, then it says the parity of the number is even. So after performing arithmetic or logical instructions, processor wanted to indicate the status whether the result is having even parity or the result is having odd parity, and that is indicated by this parity flag. So this flag is set to 1 if the lower byte of the result contains even number of ones. If the lower byte of the result contains even number of ones. This is important. It doesn't consider all 16 bits if I am considering 16-bit operation. It doesn't consider all 16 bits if I am performing 16-bit operation, because in 8086 I can even perform addition of AX and BX. These are 16-bit numbers which will generate 16-bit result of addition. But will it see the 16 bits of the result to check the parity is even or odd? The answer is no. It will check only lower order byte, lower order 8 bits to say whether the parity is even or odd. So this flag is set to 1 if the lower byte of the result contains even number of ones. For odd number of ones, it is set to 0. Okay, so this is a parity flag. Actually, I should quickly show you this operation uh, in a program. So let us check whether I am able to switch it over there. Just a moment. That will give you a fair idea about what exactly I wanted to say. So, okay, now I think the desktop is visible to you. I will just type CMD over here. Is all the things that I'm doing is visible to you? Like I search for CMD, it will open the black window. Is this window is visible to you?
Y-
Yes, sir.
Okay, fine. So now I will just go to TSO rather than doing this, because this will take DOSBox initialize nahi hoga. Instead of that, I will search for TSM software itself. So this is a TSM software 1.4 for 64-bit operating system. I will just click on it. By that time, can you find out two operands, 16-bit operands, where the parity will be even? Parity of the result will be even. Can you just find out two 16-bit operands? When I add them, parity of the result should be even. So I will just go to edit. It will open a blank window. So as you know, we need to use the command model .model small at the beginning. This is compulsory. Data segment, stack segment, they are not compulsory, so I will skip them. Directly I will write .code. I will write the code segment. Inside that we require .startup. So I will write .startup as the initial command. And now I will load Ax register. Like I will write move Ax comma some number. Let's say the number that I will load into Ax register is 8080H. So if you know the binary format of 8080H will be 1000, this is 8, then 0000, this is 0, then again 1000, this is 8, and 0000 will be 0. So 8080 is a 16-bit number which I have loaded into Ax register. Then I will load some another 16-bit number into Bx register. Let's say Bx, and then I want the result something like this, where this is the higher byte, and let's say this is the lower byte. So I wanted to have the result something like this, or let's say this I will make 1. So what is the parity of this 16-bit number, 16-bit result? If I ask you the 16-bit number that I have typed, if I am expecting this as a result, what is the parity of this result?
Even parity, sir.
Even parity. But in our case, this will not set parity flag. Why? This is what I wanted to make clear to you all, that this 16-bit number is having even parity, but 8086 processor, when it want to set the parity flag, it doesn't consider all 16 bits of the result. It considers only lower 8 bits of the result. So if you see the lower 8 bits, these are the lower 8 bits of the result. And if I ask you what is the parity of these lower 8 bits, you will find there are only 3 number of ones. That means the parity will be odd. So even if I perform this addition, the parity flag will not be set. Is the point that I wanted to make is clear to all? To get this result, by the way, what should be the second operand? It can be something like this. Let's say 0, 0, 0, 0, 0, then 1, 0, 0, 1, and then here it should be 00000011. So what is this number? This come to be 0903. So 16-bit number that I wanted to load as the second operand, 0903H. This will be the second operand that I am using. And now if I perform addition, to perform addition I can write add Ax comma Bx. So it will perform addition of Ax and Bx. So this result will be stored into Ax. As per our normal logic, the parity flag should get set, because if I see the 16-bit result, the number of ones are 6. That means it is even. That means it is even parity. But 8086 processor doesn't do it. It doesn't consider all 16 bits of the result to say what is the parity. It considers only lower order 8 bits to indicate the parity. So after this, to terminate the program, if you remember, I have to load move ax comma 4c00h, and then I have to execute interrupt instruction interrupt 21h. So this int21h is the instruction, and this is something called as software interrupt, which I have told in the feature that 8086 processor supports 256 software interrupts. One of them we are regularly using in all program, that is interrupt 21h. And after this, at the end, to end the program, what we should do is we should write the directive dot end. Dot end will indicate end of the program. So I have written a very simple program to just get the idea about a parity flag. This is a demonstration program. It is not doing anything useful, but to give us the idea that how the processor operates or considers the parity of the result. Let us save this program by giving some name. Let's say par.asm. Par stands for parity. Okay, so I will save this program. Then I will exit this editor window. Let us write CLS so that I will come on the top of the screen. And you know the process to assemble the program. You have to write TASM, name of the program, let's say PAR, extension should be .asm. So I will run the program .end. No, it should be only end. So I have made a mistake. So I have to again edit my program. Edit. I will write par.asm, and then it should not be .end. It should be only end. So I will save it again. I will exit, and then again I will assemble. So you can see this time there is no error. So error messages none, warning messages none. I will again clear the screen. I will link my program. So let's say T-link. I have to write PAR. No extension is required. When I press enter, so it will link my program with one warning, that is no stack. It is okay. I'm not using any jump instructions. So not having stack is not a problem. Then I can debug my program by writing TD, and then I have to write par.exe. It is very important. Whenever you are debugging a program, you should specify file name with .exe extension. Otherwise, it will not be debugged, right? So when I press enter, a new window will open in front of me. Let's say, okay, program has no symbol table. Okay. And I already told you, don't worry about execution of instructions up to STI. So इसके just previous instruction STI थे, तो STI तक I reached by pressing F7 continuously. You have to press F7 key continuously so that you will reach STI. Don't scroll up down key से scroll मत करो. That will not execute the instruction. You have to go down by pressing F7 key continuously. So once you reach here, that is fine. Now I will press F7. So it has executed first instruction, that is move AX 8080H. If you remember, that is the first instruction that we have written. And so you can see here, Ax register is now loaded with the number 8080. Right? What is the BX right now? BX right now is FFD0. When I execute this instruction, move BX, 0903, this FFD0 will be replaced by the number 0903. So let us execute the instruction. Now you can check. The BX register is loaded with 0903. Right? Now we are about to perform addition. If I execute this instruction by pressing F7, it will perform addition of AX and BX to create the sum, and that sum will be stored again into AX. But before we do that, let's have a look at the flags, current flag status. If you find P flag is here, P stands for parity. Right now the parity flag is clear. Okay, right now the parity flag is clear because by default after reset parity flag will be cleared by the processor. So by default parity flag is clear, right? Now when I execute add instruction, you have to observe the result stored over here and you have to observe the status of parity. Now there are two possibilities, either parity will be 1 or parity will be 0. If I consider the rule that the parity will be calculated by considering all bits of results, then definitely P should be 1, because all bits of result, if I observe, just now we have seen in the editor, there are 6 number of ones in the result. So P bit should be 1, indicating that parity is even. But the second possibility is the parity flag will be clear because the processor doesn't consider all 16 bits of result. It considers only lower byte of the result, lower order 8 bits. And in that lower order 8 bits, you will find there are just 3 number of ones. That means parity flag will be clear. Is this clear? So which option is correct? According to 8086 processor, second option is correct. 8086 processor doesn't consider 16-bit parity. It considers just 8-bit parity. Let us execute the instruction add. So you can see the result created is 8983 and you will find parity flag is still clear. Now this will indicate that 8086 never calculates parity for 16 bits. 8086 always calculates parity for only lower order 8 bits. Have you understood this or not? Is the point clear to all? Because this can be a question in the practical examination by the external examiner.
Yes, sir.
Okay. So let us see another case, reverse case. So I will just terminate this program. I will change my operands and then we will see the other possibility. We will say no. We will quit the debugger. I will again go into the edit option. I will edit a program par.asm. This time what I want is this 0. So if I want 0 over here, that means this bit should be 0, right? And then second thing that I wanted is this should be 1. So that means this should be 1. Oh no, we will keep this 0 only. I want to get this result. So this is 0901H, right? If I perform addition of 8080 and 0901H, of course the answer will be 8981H. And if you see the parity of the result now, total result का अगर मैं parity देखता हूँ 16 bit का, so it becomes 1, 2, 3, 4, 5 ones are there. That means it indicates it's a odd parity. But processor will not say this is a odd parity because it doesn't observe all 16 bits. Rather, it observes only these 8 bits. And in these 8 bits, the number of ones are just 2. That means it is even parity. So according to 16-bit rule, P flag should be 0. But according to 8-bit rule, P flag should be 1. We will just check it. We will save this. I will exit the editor. Again, I will assemble my program, link my program, and debug my program. Okay. Now, again, the same thing. Up to STI, I need not have to worry. I need not have to observe anything. So STI तक directly जाएंगे हम लोग by pressing F7, of course. Then let us execute this instruction. Right now AX is 0000. If I execute this, it becomes 8080. Execute this instruction. Then BX becomes 0901H. Observe parity flag. It is 0. I am going to add. So as per the 16-bit rule, parity flag should remain 0. But as per the 8-bit rule, the parity flag should get set. Let us check what happens. If I execute this instruction, what you will find? The result is 8981H. The parity of the total 16-bit is odd. So ideally parity flag should be 0. But this is not the thing the 8086 does. It checks only the parity of lower order 8 bits. And therefore, the parity flag is set, indicating the parity of lower order 8 bits is even. Now, I hope this point is clear to all and you will never forget. Is this clear to all?
Yes,
Yes,
sir.
sir.
Okay, so everybody is, I think, is compatible with this particular logic. So this type of small programs we can write at any time to demonstrate that whatever we are learning is very much can be seen directly by going through the execution of the instructions. So I hope you have written about the parity flag. We have completed carry flag, we have completed parity flag. The next flag is auxiliary carry flag. You give the name auxiliary carry flag in your notebook. This is an interesting flag. This flag will be set if there is a carry from the lower nibble to the upper nibble. This flag will be set if there is a carry from lower nibble to the upper nibble. That means the third bit of the operand. So this is the third bit. If you see, actually it is in the fourth position. Index is 3, but the position number 1, 2, 3, 4. Position number is 4. If the fourth bit, this is a nibble. If the fourth bit in the result forwards a carry to the upper nibble, then the auxiliary carry flag is set. Or in case of subtraction, if there is a borrow from higher nibble to lower nibble, then it will set the auxiliary carry flag, otherwise it is reset. So write the explanation quickly. We will see the example also, demonstration also. Have you written the explanation? See, only reading and listening will not help you to remember the things unless you do not write them in your notebook. So, reading, listening, watching, and writing, these all things are required if you want to remember the information for a longer period. So, therefore, I am insisting on writing. This is one reason, and of course, second reason is uh, whenever we are completing the topics, by the time you will have a good set of notes ready in your notebook. So at the end, you need not have to run here and there for the books to get the answers. They will be ready in your notebook. Have you completed the explanation of auxiliary carry flag?
Yes, sir.
Okay. So let us again go back to our DOS box. I think it is visible now. We will write again a small program. So I will edit the same program. In the same program, I will make the changes. Let's say par.asm. Now, we want the operands specifically where the carry generated, getting generated from lower nibble to upper nibble. So let us consider 80 as one of the operand. No, not 80. I should have the fourth bit set so that it will generate carry. So let's say 89H is one of the operand that I will store not in AX because 89H is not a 16-bit number. It is a 8-bit number. So I will use AL. And the binary format for 89H will be something like this. 1000 is 8. 1001 is 9. So this is 8, 9 in binary. I hope everybody is comfortable in this conversion. You have to remember binary bit patterns for A to F. You have to mug up them and you have to be fast enough to understand the binary pattern for that number. Then I will take second operand. Let's say second operand I will take is A, uh, write in lowercase, uppercase is also supported, A8H. So if I want this 8-bit number as the second operand, so how to write A8 in binary? A means its binary pattern is 1010. This is A and 8 means it is 1 0 0 0. So this is A8 in binary, and I wanted to perform addition. So of course it should not be stored in BX. I can store it in either BL or BH, and then add instruction will change. It will be now add AL comma BL, because 8-bit operands I am supposed to add. By the way, can we perform addition manually to get the result? I will remove this from here. So addition will be performed bit by bit. 1 plus 0 will be 1. 0 plus 0 will be 0. Then 0 plus 0 will be 0. Then 1 plus 1. This is the fourth bit. 1 plus 1. It becomes 1 0. So 0 will be kept here and 1 will be forwarded as a carry. Now this carry is important. Are you getting which carry? This is the lower nibble of the operand. So if I perform addition of two lower nibbles, then the carry is generated and it is forwarded to upper nibble. So here I will get one carry. So it is 0 plus 1 carry. So result will be 1, right? 0 plus 0 plus 1. Then 0 plus 1 is 1. Then 0 plus 0 is 0. And then 1 plus 1 is 0. And the carry is forwarded. So lower nibble has forwarded a carry, as well as upper nibble has also forwarded a carry. So this carry, that is carry forwarded by upper nibble, the status whether it is there or not is indicated by using carry flag. So carry flag will be set because of this carry, and auxiliary carry flag will be also set because this 1 plus 1 is resulted into 1 0. Out of 0 is here and 1 is forwarded as a carry. I hope you are getting whatever I am explaining. Okay, so when we run this program, we should observe carry flag as well as we should observe auxiliary carry flag, right? But before I assemble this program, I should recall one rule, that whenever we wanted to specify some number which is starting with the alphabet, like this number is starting with alphabet A, then you should have a prefix, 0 prefix before it. If I do not use this 0 prefix, this will generate error. Let us remove this 0 prefix first and assemble the program to see the error. Let us save this change. I will exit the editor and I will assemble my program again. Let's say tasm par.asm. So you can see this is giving me error. And what error it is saying? Error par.asm. In bracket they have written one number, that is 5. That means in line number 5 there is an error. So this number is important, which is coming in the bracket, because if you want to remove the error from the program, you should exactly know that where is the error, in which line there is an error. So the assembler will help us in this respect. It will specify line number where there is an error, and what error it is saying, undefined symbol A8H, because we want this should be considered as a number and processor is trying to treat it as a name of some register. So if the numbers is starting with alphabet, you have to prefix it with 0, right? Let us again go back to the editor. I will write edit. The name of the program is par.asm. Again we are back into the program. So you can see this is line number 1, 2, 3, 4 and 5. This is line number 5. In this line the assembler is saying that there is some error, and you have to find out the error in that line only. So we have to prefix it with 0. Adding 0 on left hand side of the number doesn't change value of the number. It still remains A8H, but it helps the assembler to understand that this is not the register starting with A, but this is a number because we prefixed it with 0. So let us save this. Let us again exit the editor and assemble our program. This time you can see, if by making that change, now the assembler is saying there is no error, there is no warning. I will just clear the screen. We will link our program again. See, every time you make the change in your program, you should assemble it, you should link it, and then you should debug it. Do not debug directly, because the changes are required to be assembled, they are required to be converted into machine language, and then only you can debug it. Every time you make change in your program, it is compulsory that you should assemble it, link it, and debug it, right? So I will link it, and then finally we will debug it by writing command td. Okay, so when I write td, it will open a debugger window. Again, I have to jump, or I have to keep on executing instructions till I do not reach STI. STI तक ऐसे ही पहुंच जाना है by pressing F7 key without observing anything else. After you reach STI, you should be alert and you should be watching the changes that is happening because of your instructions in the program, right? So right now you can see AL is 00. If you observe over here, these two digits indicates contents of AL and these two digits indicates contents of AH. Together combined, it will form AX. So I already explained during the software model that the general purpose resistors provides us the flexibility of making use of them either as 8-bit resistors or as 16-bit resistors. So I am just taking advantage or use of this particular flexibility. So when I execute move AL, 89H, you can see AL will be loaded with 89H and AH will still remain 00. So AH is not modified, only AL is modified by the number 89H. I can load another number A8 into BL. If I execute that instruction, you can see only BL will get affected. BH will still remain same. So I will execute by pressing F7. Have you observed that BH is not affected? Only BL is affected. Now it is holding other operand A8. And now I wanted to perform addition. Before we perform addition, we should check carry flag. We should check auxiliary carry flag. So here is a carry flag which is right now clear. And here is auxiliary carry flag which is right now clear. After the execution of my add instruction, both should get set. And why? I already explained in the editor. Let us execute this instruction, and what you will find, carry flag is set to 1, auxiliary carry flag is also set to 1. That means during the execution of this addition instruction, what the processor has recognized. Processor has recognized that lower nibble has forwarded carry to upper nibble, as well as upper nibble has also forwarded carry to the carry flag. So both the carries are generated. So C is equal to 1 and A is equal to 1. I hope this demonstration is clear to all. Have you understood when the auxiliary carry flag is set? Have you got the idea about auxiliary carry flag?
Yes, sir.
Okay. So I will just complete the execution of this program. I will quit this and I will again enter into edit mode. I will open my file whose name is, let's say, par.asm, and now I will take the operand in such a way that lower nibble will not forward any carry. So to take that kind of operands, what I should do is I should make this bit 0. So if I make this bit 0, what will happen? 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 0 is 1. It will not forward carry. That means auxiliary carry flag will not be set. 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 1, 0. So 0 will be here, 1 will be forwarded as a carry. That means lower nibble has not generated any carry, but upper nibble has forwarded a carry. So it will not set auxiliary carry flag, but it will set only carry flag. Let us have this change. To make this change effective, the second operand I should take A0H. So first operand is 89H, second operand is A0H. Let us save this change. This is also important. Every time you modify the program, you should save it, because without saving, if you assemble it, it will not assemble the changed version. It will assemble the previously saved version, and you will not be able to see the effect of the change that you have made. So these are very small things, but you should be very careful about them. Every time you make a modification to the program in the editor, what you should do is you should save it, and then you should exit the editor, and then again you should assemble it, then you should link it, and then you should debug it. How I'm getting these commands again and again? Just by pressing up and down key. Up and down key will allow you to move through the list of commands that you already delivered. So that is a DOS feature. You can get back to any command that you have previously given by just pressing up or down key of your keyboard, right? So you need not have to type the command again and again. Up and down key will keep on bringing all the commands. For example, if I press up key, it is bringing t-link command, cls command, tsm command, edit command. So it will rotate in a round robin fashion. 4-5 कमांड ही मैंने दिया है, तो उनके बीच में वो रोटेट करता रहेगा. जो कमांड तुमको चाहिए उसको सिलेक्ट करके रखो एंड देन प्रेस एंटर. So this will debug my program. Again, I have to move on directly up to STI without watching anything. When I write move 89, AL will be 89, BL will be A0. Observe carry flag and auxiliary carry flag both are 00. When I perform addition, what you will find this time is carry flag is set, but auxiliary carry flag will remain 0, which indicates the carry is not generated by lower nibble. Carry is not forwarded by lower nibble to upper nibble. Now I hope you have understood the auxiliary carry flag, when it will be set, when it will be clear, right? So I will just quit this. We will get back to our presentation. So auxiliary carry flag, when it will be set and when it will be clear, we have written. But what is the use? Why the processor indicates this status? What is the practical use of this flag? Like carry flag, if I ask you what is the practical use of a carry flag, you will say the carry flag, if it is set, it indicates that the result in the destination is not the complete correct result. It is part of the result. One bit of the result is missing, and that you should consider as a carry flag. I hope, is this clear? If I perform addition of two 8-bit numbers, the result may be 9-bit number, but the destination, since it is only 8-bit register, it cannot store 9 bits. So destination can hold only 8 bits. The 9th bit is present in the carry flag. So this is the indication. When the carry flag is set, you should be aware of the fact that the 8-bit number present in the destination register is not the complete result. So uska practical significance mujhe samjha. What is the practical significance of parity flag, by the way? Because only knowing when it will be set, when it will be clear, will give you a theoretical knowledge of that particular thing. But practically how it can be used when you are writing application, that is important. What is the use of parity flag basically? Does anybody knows? I know we are towards the end of the lecture. It is almost 2.5 hours. But still, keep yourself alive and recall if you have learned or came across this particular word parity sometime before.
Sir, to check if there is any error.
Right. So parity is mainly used for error that may happen during the communication. Right. So consider the situation that there are two 8086 processors in two different systems, and they wanted to communicate with each other. They wanted to exchange some number. So one 8086 processor will send 8-bit number to second 8086 processor. So one is transmitter, other is receiver, and then they transfer the number through the communication lines. Let's say data bus, they are transferring the numbers. Because of noise, what may happen, one of the bit of the transferred number is flipped. That means actually the bit transferred is 1, but the bit received is 0. Are you getting the problem? So let us consider the example. The first 8086 wanted to transfer FF. That means all 8 ones. All 8 ones. FF it wanted to transfer. But because of communication channel error, the second 8086 has received FEH. What is FE? It will be 11111110. So transferred is FF, received is FE. That means the second 8086 processor has not received the data correctly. But how does it knows whether it has received the data correctly or not? There is a simple protocol which can be set between the two 8086 processors. The first 8086 processor, before transferring any number, the transmitter processor will say this to the receiver processor that whatever numbers I am going to send you, they all will have even parity. They all will have even parity. So by chance, if you receive any number which is having odd parity, then you have to understood that this data is received with error and you should ask for retransmission. Isn't it? Have you understood the protocol? This is called as protocol is nothing but what set of rules that is set between the two parties, that is transmitter and receiver. And they should be agreed upon this set of rules so that we can minimize the error that may occur during communication, isn't it? So one bit error can be detected very easily by using parity. Have you understood why only one bit? Because if the 2-bit flips, then transmitter will be FF, received may be FC. What is FC? It is 11111100. So there are 6 ones. That means still it will have even parity, and there is no way by which receiver will understand that transmitted data was FF and I have received FC, which is error. So 2-bit error or multiple bit error cannot be detected by using parity. Only 1-bit error can be detected by using parity. And to detect multiple bit errors, there are other error correcting codes. Have you learned any error correcting code? Have you learned any error correcting code?
Hamming code.
Yes. Pardon?
Hamming code.
Yes. Hamming code can be used. Then CRC. Have you heard about CRC? Cyclic redundancy check.
No, sir.
No. So you will learn it
Sure.
very soon in the computer network. Computer network is a part of your syllabus right now. No? It is there in 5th sem, isn't it? So error detection and correction is a inherent part of computer network, because in computer network the devices are communicating with each other by making use of medium. It may be a wired medium, that is Ethernet cable, twisted pair cable, or it may be a wireless medium by using the microwaves. But in any case, there is a chance that the transmitted data will be different than received data. Then in that case, the receiver should be in a position to understand whether the received thing is correct or it is received with error. सबसे पहले तो ये समझना चाहिए कि received thing is with error or without error. That is possible by using error detecting codes. That is possible by using error detecting codes, right? And then once the receiver understands that whatever is received is with error, then comes the next possibility that whether the receiver is able to correct it on its own, or the second option is it should ask the transmitter to retransmit the same thing. Are you getting the two possibilities? Either the receiver should be able to correct the error on its own, or it should ask the transmitter to retransmit the same thing again. So it is called as forward error correction, FEC. That is forward error correction. That is first possibility, that receiver is in a position to correct the error, and that is possible by using error correcting codes. So error detection is different thing, error correction is a different thing. So forward error correction is called as the process in which the receiver will be able to detect the data with error, as well as it is able to correct it on its own. It will not go for a retransmission, because retransmission will require more amount of time, as well as it will consume bandwidth unnecessarily, because same data is being sent again and again. So that means we are consuming bandwidth for redundant data transfers. Have you understood this simple thing? In computer network, when you go to the data link layer, the data link layer's responsibility is this, that error detection and correction. So data link layer will ensure that there is no error. It will form the frames. For every frame it will add the parity bits or Hamming bits, and then that will be transmitted. So very soon you will understand about this in the computer network. So this is not our topic of discussion, but you should get some linkage कि yes, ये सब होता है because the softwares are able to do it just because the support is provided by hardware, that is processor. Are you getting how the subjects are linked? Okay, so parity is important thing for error detection. Parity flag cannot be used for error correction. It can be used for only detecting 1-bit error, and this can be very easily done by setting a protocol between transmitter and receiver. So I hope you have understood practical use of parity flag. Now we will come back to the auxiliary carry flag, and we will just discuss briefly what will be the practical use of auxiliary carry flag. So this is practically used whenever we want to perform BCD arithmetic. Have you heard this word BCD? BCD?
Yes, sir, in DLDA.
Yes. What is BCD means? It is binary coded decimal. BCD means binary coded decimal. So if I want to perform addition of two BCD numbers, and if I expect the result to be BCD, then it may not be possible directly in 8086 environment, because 8086 processor treats every number by default as a hexadecimal number. 8086 processor considers every number by default as a hexadecimal number. That means if I perform addition of let's say 7 and 9, so 7 is considered as hexadecimal, 9 is considered as hexadecimal, but I wanted to consider that as a BCD numbers. So I expect a result 7 plus 9, 16. But processor will not give you 16 as a result. When I perform addition of 7 and 9, the result provided by the processor will be 10H. Are you getting how? If you start counting ahead of 9 or 7 times, so after 9 what comes in hexadecimal? It is A, then B, then C, then D, E, F, and after F what comes is 10. So you can perform hexadecimal arithmetic manually by using your fingertips. You have to count on your fingertips, right? So 9 ke baad aata hai, because I wanted to add 7 into 9. So I have to count 7 these parts of my finger. So after 9 what comes is A, then B, then C, then D, then E, then F, and 10. So 7 plus 9, the result calculated by 8086 processor will be 10H. It will not be 16H. It will not be 16 decimal. And I wanted to get it as a 16 decimal. Are you getting the problem? In this case, the auxiliary carry flag plays important role. If I want to perform BCD arithmetic, and if lower nibble has forwarded carry to the upper nibble, it means the BCD result lower nibble is exceeding the 4-bit capacity, and we need to adjust it. This adjustment can be performed by adding 06 in the result. So actually calculated result is 10H. If I add 06 into it, then it will become 16H. And this is performed by using instruction called as DAA, that is decimal adjust accumulator. So in DAA instruction, you will actually get the practical use of auxiliary carry flag. But I hope the situation is clear to you. If somebody asks you what is the practical use of auxiliary carry flag, then you can definitely be able to say that it is mainly used when we want processor to perform BCD arithmetic. How it uses it, which instruction can be used, that is a second part that we will see in detail in the instruction set. But right now, when somebody asks you what is the practical use of auxiliary carry flag, you should be in a position to answer that it is mainly used when the processor is performing BCD arithmetic. Is this clear? We will go to the next flag quickly, that is zero flag. This is not a difficult flag to understand. Many of you might be knowing. After performing arithmetic or logical operation, there is a chance that the result created will be zero. So if the result of any arithmetic or logical operation is zero, then the processor will set this flag. Otherwise, this flag will be cleared. So you can write the explanation of the zero flag. This flag is set if the result of the computation or comparison performed by the instruction is zero. So अगर result zero है तो zero flag 1 होता है. ये याद रखना जरूरी है. Result zero है तो zero flag 1. Result non-zero है, zero flag will be 0. Non-zero result is indicated by zero flag equal to 0. Zero result is indicated by setting zero flag equal to 1. It is very simple flag. Then next flag is a sign flag, and its name itself will suggest you this flag indicates whether the result of the sign of the result is positive or sign of the result is negative. So if this flag is set by the processor, this is a control flag. So it is a status flag. So processor has to indicate the status. So if the processor sets this flag, which indicates that the result of computation is negative number, and if this flag is 0, it indicates that result of computation is a positive result. So this flag indicates the status of the result, whether it is negative result or positive result. It is important in case of comparison. Zero flag and sign flag, they plays very important role whenever we are comparing two numbers. For example, I wanted to check the relationship between the two numbers. If I want to check whether the 90 is equal to 90, so compare instruction, what it will do, simply subtract 90 from 90. What is the result? Result is 0. It is indicated by using zero flag. So when zero flag is set, after compare instruction, if the zero flag is set, I have to understand the operands that I am comparing are equal. But if I ask to compare 90 with 80, then compare instruction will subtract 80 from 90. So 90 minus 80, it will become 10, which is a positive result, which indicates the first operand is greater than second operand. This is indicated by sign flag equal to 0 and zero flag equal to 1, because zero flag equal to 0, sign flag 0 and zero flag 0. So if both are 0, which indicates result is non-zero and the number is positive, that means first operand is larger than second operand, right? And the third possibility is if I want to compare 80 with 90, then in this case 90 will be subtracted from 80. The result will be minus 10, which is indicated by setting sign flag. Zero flag will be 0, which indicates result is non-zero because it is a negative number, and sign flag will be equal to 1, which indicates result is negative, and we can conclude that first operand is smaller as compared to second operand. So in case of comparison, sign flag and zero flag plays very important role. So I hope you have understood significance of sign flag and zero flag, right? Now, have you written the explanation of sign flag also? This flag is set when the result of any computation is negative. Simultaneously, you should keep on writing notes. That is important. Again and again, I am giving you a reminder, because if you do not write anything, at the end, you will find nothing is there with you to recall the things or revise the things for the examinations, IR test, or you can say the quizzes that I am going to conduct. Right? So you should have these all things mentioned in your notebook. The next flag that we will discuss is a trap flag. So it is by mistake written as TARP. Correct it. It is TRAP, trap flag. So there is a typing mistake. TARP nahi, TRAP, trap flag. This is a control flag. That means this will not be set or cleared by the processor. This is required to be set or cleared by the programmer. So if the programmer sets the trap flag, then the processor enters into single step mode. If the trap flag is set by the programmer, Programmer has to set it. If we set trap flag to 1, then the processor enters into single step execution mode, where after execution of every instruction, an interrupt is generated automatically. And in the interrupt service routine of that interrupt, the instructions are written to display the contents of all the registers, so that we can debug our program. Instead of executing all the instructions all together, what we are doing is we are executing one instruction at a time, and we wanted to check the result of that instruction, whether it is yielding me the correct result or not. This is called as what? Single stepping, which is a debugging method, and which, if you remember, we are using when we are debugging our program. Just now we have used it, pressing F7. When I am executing the program, what I am doing is I am pressing F7. Pressing F7 will automatically insert interrupt instruction after every instruction. So एक instruction execute होता है और interrupt generate होता है, and then the processor will display the contents of the register. So I can check whatever modifications I wanted to do by that instruction, are they happening or not. So if it is not happening, that means I made some mistake, logical error in that instruction, and then I have to correct it. So debugging is a very handy tool for removing the logical errors, whereas assembling is a tool which is used for removing or detecting the syntax errors. Compiler or assembler, they are meant or they are designed for detecting syntax errors, whereas debugging is required for detect and remove the logical error. Are you getting the difference between syntax error and logical error? Logical error means there is no any grammar mistake I am doing, but it is semantic mistake and I am not getting the expected result. So because of that logical error, I am getting the incorrect result. Instruction will be executed, no doubt, but the result is not correct. So that type of errors can be removed by using the trap interrupt. Trap flag is important. So you have to set the trap flag that will ask the processor to enter into single step mode or single step execution mode. So you can see control flags are set or cleared by the programmer to control the actions taken by processor. So if I set the trap flag, processor will take action. After every instruction, it will execute interrupt and it will show you the contents of registers. But if I clear the trap flag, processor will not generate interrupt after every instruction. It will execute all the instructions present in the program all together, and it will show you the final result. So trap flag is a control flag. So I hope you have written about the trap flag. Let us move on to the interrupt. Just we will finish this flag register and then we will stop for the day, because I know we are closing to the end of the third hour. It is almost 2 hours 53 minutes. So in a 7 minute, I will try to complete this so that we can end this session. So interrupt flag is again a control flag which is under the control of programmer. Programmer can set or clear interrupt flag. If this flag is used by the programmer, it is used for controlling the or enabling or disabling of the interrupt. So if I clear this flag, then external interrupts are disabled or they will be masked. So if I make these flags if I set it equal to 0, then any interrupt signal coming on INTR pin will not be recognized by the 8086 processor. It will be simply ignored because we are masked. But if I set it to 1, then interrupt will be enabled and interrupt signal coming on INTR pin will be recognized by the processor. So IF equal to 1 allows the processor to recognize interrupt coming on INTR pin. IF equal to 0 does not allow processor to recognize the interrupt coming on INTR pin. If you remember, there are two hardware interrupts, two interrupt pins, INTR and NMI. At the beginning of this session, I have just touched that topic. NMI cannot be masked because its name itself is non-maskable interrupt. So IF flag, interrupt flag, doesn't have any effect on NMI pin. This is a very important thing that you should remember. IF flag can have effect only on INTR pin. IF equal to 1, INTR is enabled. IF equal to 0, INTR is disabled. So this is as simple like this. Then we will go to the next flag, that is called as a direction flag. D flag stands for direction. This is related to the string manipulation. You know, string is a sequence of characters, and I can process the string either by moving from left to right, that is first character to last character, or even I can process the string by moving from last to first, that means right to left. So 8086 provides you the facility to decide the direction in which you wanted to process the string, whether you want the processor should process the string from left to right, or you want the processor to process the string from right to left. This option can be selected by using direction flag. So if this flag bit is cleared, that means if I write df equal to 0, agar मैं ये bit clear करता हूँ, then the string will be processed from left to right. That means lowest address to the highest address. But if I set this particular flag, if I set a direction flag, then the string will be processed from right to left. That means highest address to the lowest address. Now what does this means actually? We will see, because this is related to SI and DI also. Whether SI will increment automatically or decrement automatically, that is decided by this direction flag. If D direction flag is equal to 0, then SI and DI will be auto incremented, and if it is set to 1, then SI and DI will be auto decremented. So what is this auto increment, decrement? We will see in detail when we will go to the string related instructions. By this time you should remember that direction flag is a control flag. Programmer can set or reset it. If the programmer sets it, string will be processed from right to left. If the programmer resets it, string will be processed from left to right. That means first character to last character, right? Now the last flag that is remaining, that is called as overflow flag, and the name itself gives you idea. If we perform some arithmetic or logical operation and the result is bigger and it cannot be accommodated in the specified destination, if the result cannot be occupied in the specified destination, then this will be considered as overflow, and the situation will be indicated by setting overflow flag. So this flag is set if an overflow occurs, that is if the result of a signed operation is larger to accommodate in the destination register. Because you see, when I say a particular operand is signed or unsigned, that will change the magnitude of the number. Because if I say the 8-bit unsigned number, then all 8 bits are used for storing the magnitude. If I say I am talking about 8-bit unsigned number, then all 8 bits are considered for storing the magnitude of the number, because sign is not required to be stored. It is by default positive, since we are saying it is unsigned number. But if I say 8-bit signed number, if I say 8-bit signed number, then all 8 bits cannot be used for storing the magnitude. Only lower order 7 bits will be used to store the magnitude. 8th bit is used to indicate sign. If that 8th bit is 1, it indicates the number is negative number. If the 8th bit is 0, it indicates the number is positive number. So whenever we are talking about signed arithmetic, when we add two 8-bit signed numbers, now this is very important, 8-bit signed numbers, then if the result is not possible to accommodate in 7 bits of the destination, 7 bits of the destination, not 8 bits, because signed arithmetic only 7 bits are used for magnitude. So if the magnitude of the result cannot be accommodated in 7 bits of the destination, then this overflow flag will be set. This is something different than carry flag. Are you getting? Carry flag, when I add two 8-bit numbers and if the 8th bit is forwarding carry, then it will be considered as carry, not overflow. But if I am performing arithmetic on 8-bit numbers and 7th bit addition is forwarding carry, then it is called as overflow. Or in case of 16-bit arithmetic, if 15th bit is generating carry, then it is called as overflow. So theoretically, I hope little bit things are clear to you about this overflow flag. Practically, we will see how or when this overflow flag or is set or it will be reset. and how it is different than carry flag during our practical session, which will be tomorrow. So I hope whatever we have discussed in the today's session is clear to all, and you have prepared nice notes out of this particular session, which you will read again before coming to the next session. So you will recall all the things that we have discussed. So we will continue with our discussion about remaining topics in the next session. For today, we will call this as a end of the day. So today's discussions we will stop here. I don't know why today the attendance is less. I can find only, just a moment, don't leave, only six people are attending. I don't know whether they are absent or they are attending in Arun Chavan sir's session. If they are attending over there, absolutely no problem. So anyway, so thank you for being here for continuous 3 hours and listening to this particular discussion. So now you can leave the meeting. I will just stop the recording. This recording will be available to you on Microsoft Stream. You can revisit, you can watch it any number of times.